Welcome everyone. It's 4 o'clock now in Taiwan. And today's speaker is Professor Junichi Kurihara, Associate Professor in the Faculty of Business Administration and Information Science of the Hokkaido Information University. But he's an expert on microsatellite, on remote sensing, and as you will hear, on atmospheric physics and thermospheric physics. Professor Kurihara, he got his college and PhD degrees all from University of Tokyo, and afterward he spent some time working in Hokkaido, the Hokkaido University, and now he's as I said earlier, he's now the associate professor there. Specializing in doing nano satellite and also coupled with hyperspectral imaging. And because of hyperspectral imaging, he could do a number of very interesting, important things. And I can read it from his CV. He's been talk about diagnosis of some disease, isn't it? I mean, that is also very interesting. Maybe I will ask you to give a talk some other time on that topic. but today, please talk about the nano satellite.
Okay.
Yeah, in remote sensing. Yes, Professor Kurihara, please start your talk. Thank you so much.
Thank you, Professor Abe. Hi, everyone. I'm Junichi Kurihara, and today I'd like to talk about the optical remote sensing of the Earth from nano microsatellites. So first of all, I'd like to introduce myself. I'm Junichi Kurihara. Now I'm working at Hokkaido Information University as associate professor, and before that, I was working in Hokkaido University, a different university, and for 12 years. And at the Hokkaido University, I was involved in several microsatellite projects, including Rising 2, Givata 1, Givata 2, Microdrone, LISAT, etc. And some of them are international collaboration with between Japan and other Asian countries like Philippines, Vietnam, and Taiwan. And now my research topic is remote sensing, especially hyperspectral imaging and Earth observation. So this is the contents of today's talk. First, I'd like to talk about the introduction to optical sensors. And next, history and trends in Earth observation. And then development of optical sensors, and on-orbit calibration and data management. And finally, I'd like to conclude. So first topic is introduction to optical sensors. As you know, light is detected by different types of detectors, depending on its wavelengths. And in the visible and ultraviolet range of light is detected by photomultiplier tube or PMT, and also visible lights are detected by silicon photodiodes like CCD and CCMOS images, which are very familiar to us. And you may have the smartphone, CMOS image sensor in your smartphone or digital camera. And in the longer wavelengths, such as near infrared or short wavelength infrared, is detected by special substances such as indium gallium arsenide or InGaAs photodiodes. And the much longer wavelengths, such as the mid wavelengths infrared or long wavelength infrared is detected by some detectors such as indium antimonide or mercury cadmium telluride, and they are cooled detectors. So you have to cooling, do cooling of the detector. Otherwise, that cannot detect the light without noise. And in the summer infrared is detected by microbolometer, which is uncooled detector. So it's very good for the application. And there are many summer cameras which uses this microbolometer for its detector. And for the optical sensors, there are many types of the optical sensors, and but their spectral range and spectral resolution are different. In the range of the visible light, most familiar sensor is the RGB sensor, which can detect the light in red, green, and blue. And in adding these some few bands, we can get a much spectral sensor, usually more than 3 colors. And the more numbers of the spectral bands called hyperspectral sensor, which continuously detect the light from visible to near infrared with many, more than hundreds of bands. And the thermal infrared sensor can detect the thermal infrared band, and it is used for the thermography. This is a spectral bands of the famous Earth observation satellite Landsat. And as you know, the Landsat has many generations. The first generation is Landsat 1, and now the latest is Landsat 9. And first generations from Landsat 1 to Landsat 5 has only 4 bands multispectral sensor in visible to near infrared. And after that, Landsat 5 has also has a 7-band sensor, and the Landsat 6 was failed, and Landsat 7 had a 8-band, and now Landsat 8 and Landsat 9 has 11 bands. So as you can see, the number of spectral bands are increasing, and this gray color shows atmospheric transmission, and the spectral bands are located where atmospheric transmission is high, because we want to see the surface from space. Except for this band 9, this is a band for the to detect the water vapor, to see the cloud on the Earth. And this is our specification of the optical sensors, and the most important specification is the spatial resolution and the field of view of optical sensor. And field of view is determined by the size of the sensor and focal length. So field of view can be calculated very simple equations like this. On the other hand, spatial resolution is determined from the these sensor and also the altitude of the satellite. So the spatial resolution or ground sample distance, GSD, is determined by this equation, and it is calculated from the altitude and focal length and the size of the pixel of image sensor. And the imaging methods is different depending on the satellites. However, most of the Earth observation satellites, actually more than 95% of satellites, are using push-broom imaging, which use a line sensor, and it scans ground surface with its moving. So it's like a copy machine. So the satellite is looking in the view, and the instantaneous field of view is this line, and that scans the ground surface. But some small satellites uses a two-dimensional imaging because that has a two-dimensional image sensor, which is very not expensive. And in case of two-dimensional imaging, the camera doesn't need to see the navier. It can change the direction, so it can be used for the target pointing on the Earth. So second topic is about history and trends in Earth observation. Satellites are usually categorized its weight, and generally less than 1,000 kilograms is categorized to the small satellite, and the heavier satellites are called large satellite. And in the small satellite, there are pico, nano, micro, and mini satellites. And it's the smallest one, pico satellite, is less than 1 kilogram, and the nano satellite is from 1 to 10 kilograms, and micro satellite is 10 to 100 kilograms. And the development time also depends on its weight of the satellite, and usually in the case of microsatellite, it takes from 1 to 2 years for development. And the cost is also depends on the its weight, and in case of microsatellite, it costs about 1 million USD or 30 million TWD. And so the small satellites can be developed in the short time and very low cost, and so we can increase the number of satellites easily. And the spatial resolution of the satellite has been improved with time. And in 1970s, when the Landsat 1 was launched, it has only 80 meters resolution for 1 pixel. So Landsat 1 cannot detect the house. It's less than usually it's less than 80 meters. And in the end of the 90s, its size is spatial resolution is about 10 meters. So we could see the shape of the house. And now we have the spatial resolution less than 1 meter and sub-meter sensors. So you can see the chimney on the rooftop of the house. And the spectral resolution, or number of spectral bands, also has been improved. This figure maps the spatial resolution and the number of spectral bands in one figure. So color shows the year of launch of the satellite, and the size of the circle shows the satellite mass. So larger satellite has larger circle. And as you can see, this line is mainstream of the satellite, which has 4 bands in number of bands, and but resolution is getting higher with time. So, and the number of bands also increases with time. And our satellite is here, so we have high resolution and large number of bands using microsatellites. And in the 2010 or 2015, there are large satellite constellation, and this one is East Spring constellation. Consists of many large satellites, actually 7 or 8 satellites, and it has the same orbit and with several minutes apart each other, and but they have different sensors. So this 8-ring constellation can detect the same place with many different parameters, physical parameters. However, it took more than 10 years to create this satellite constellation, because large satellite is very difficult to launch and develop. So it takes many time as expected. And now is the era of small satellites. And this is a Planet 3U CubeSat Dove constellation. And this has, Dove is only a 3U CubeSat with a weight of 3 or 4 kilograms. And they have, Planet Corporation has more than 200 Dove satellites on orbit. So it can take image of the Earth with several, actually 90 seconds apart. And so Planet provide the image of the Earth's surface for every day. So this is a quite different, technology compared to the large satellite. Usually, large satellite has 16 or 14 days of the period of time, but now we have our image of the same place every day. And this Dove CubeSats is evolving, because this one is the first generation of Dove satellite. It is called the Dove Classic, that has only 4 bands, RGB plus near infrared. The second generation, Dove R, has also has a 4 bands, but it's separated. So the resolution, spectral resolution is higher than the first generation. And now the third generation, the latest generation, is called the Superdome, which has 8 bands. So it's like a Lancer, and in the visible and near infrared range. This is another example of the CubeSat, ESA's 6U CubeSat 5SAT. It can detect the volcanic eruption using the AI deep learning technology, and if that satellite detects the volcanic eruption, it will send the image to the ground. And this is a very good idea because data transmission rate is very low for the small satellite because its antenna is very small. So such kind of the onboard processing is very important for the CubeSats. They use Raspberry Pi for this deep learning technology. So next topic is about the development of optical sensors. We have developed several optical sensors. This is an example of that, and this is called the Ocean Observation Camera, which was installed on the LiSat microsatellite. Ocean Observation Camera was developed by Hokkaido University, Tohoku University, Periscope Corporation, and National Taiwan Ocean University, NTOU. And it has 4 cameras with different spectral bands. And here is our spectral bands of OOC. So, and the OOC1 has a 405 nanometer, OOC2 has a 490, OOC3 555, OOC4 is 69 nanometers. So it can detect the seeding of the water and in the ocean. And this sensor is very unique because it has very high ground spatial resolution. It has a 74 meters, but it's very high as ocean color sensors. In the development of this sensor, we use we consider many things. And first, we have to select a detector, and now we can choose CCD or CMOS, and they have different characteristics. CCD is very sensitive, but it's very now it's very difficult to die, and the CMOS is getting better, and it's very cheap. And also we consider about the sensor size, image size, and we also consider taking into account space problem or not. And next, we select the length of the sensor, and considering the focal length, FOV, spatial resolution, spectral range, and so on. And another important thing is customization is available or not. Usually, if you buy such kind of lens, it's called a CCTV lens, and it's not used for the space use. So we have to customize the lens using with manufacturer. And the most important thing about customization of the lens is grease. Usually grease is used in the this kind of lens, so it will be evaporated in space, and it makes contamination for the optics and other components of the satellite. So we have to remove the grease from the lens. And then we need to select a bandpass filter for OOC. And we already choose the center wavelengths and bandwidth and peak transmittance. But we also take into account its blocking performance. Blocking performance means the amount of the light outside of this spectral transmittance. So if the light from at the other wavelengths spectral range it should be smaller. So blocking performance is very important, and it also called optical density, and the optical density should be larger for such kind of bandpass filter, especially for the narrow bandpass filter. And the other than OOC, RISE-SAT microsatellite has a high precision telescope, which is a high resolution optical sensor, and this is developed by the Hokkaido University and Junichi Corporation, the National Central University (NCU), and it has a long focal length of 1 meter, and it has a 2 CCD sensor for visible and near infrared, and it used a liquid crystal tunable filter for visible and near infrared range. This is a tunable filter which uses a liquid crystal, and you can choose any band from the visible and near infrared region. And this is a liquid crystal tunable filter. It's very small, and it can change the spectral band or transmittance of this filter by changing the voltage applied to this filter. So you don't need to mechanical filtering, mechanical switching of the filter. This is the transmittance of liquid crystal tunable filter, LCTF. We have 2 LCTF. One is visible and another is near infrared. This is the visible LCTF, transmittance of visible LCTF. It has about 10 to 20 nanometers bandwidth, and you can choose any band with 1 nanometer step, and from 400 to 700 nanometers. And this one is a near infrared LCTF, and it has a wider bandwidth, but also you can choose any band from 650 to 1050 with 1 nanometer step. So how to take our image is like this, and in case of visible band, so we can switch the wavelengths, central wavelengths of liquid crystal tunable filter, like this: 443, 490, 555, 67, with 0.5 second interval. So we have 4 bands within 2 seconds, and for the near infrared band, we also switch the central wavelengths from 710, 765, 869, and 910, like this. So we also have 4 bands within 2 seconds. So in total, we have 8 bands in the within the 2 seconds. This is a sequence of multispectral images using a liquid crystal tunable filter. So we got some images, and we compared it with Sentinel-2 satellite. Sentinel-2 is ESA's Earth observation, very big satellite, and it has MSI, multispectral imager, and fortunately, we have the image at the same day. And this one is a LightSat HPT. This image is created from the 3 bands, red, green, and blue of the HPT. And this is also the composite image of the Sentinel-2. As you can see, actually the color balance is different, but we can see almost the same resolution and the spatial resolution. So, and we can see the ground objects with the same level. As you know, LightSat HPT is very cheap compared to the MSI of Sentinel-2, maybe more than 1,000 or something like that. So now I'd like to talk about the testing of the optical sensors. So most important test of the optical sensor is focus adjustment, of course. And we use a collimator to get parallel light, and we can take the image of the pinhole, and we use this image. We can analyze the size of the pinhole on the image, and we adjust the focus of the sensor. And this is a picture of the actual test of the optical sensor, HPT, and we use a collimator here. Collimator is a telescope, commercial telescope, and here is a lamp and a pinhole, and we emit the light from here, and it is detected by this sensor. Here is a mirror to reflect the light. So we can test the performance after we install the sensor on the satellite. And another important test is a radiometric regression in the laboratory, and we use a uniform source. It's using a integrating sphere, and we put the sensor here, and the image taken by this setup is like this. As you can see, there is a darker region in the corner of the image, so we can calibrate by using this image to the flat image. And also other environment tests are required. For example, vibration and shape test, and thermal and vacuum tests, and the radiation tests. It's same as the other satellite components. And next, I'd like to talk about on-orbit calibration and the data management. There are many on-orbit calibration methods. Most of the large satellites utilize onboard calibration, which uses a calibration equipment to be mounted on the satellite, such as lamps and solar diffusers. And the calibration equipment itself may also deteriorate due to the launch or aging. And this onboard calibration is difficult for small satellites. Another method is vicarious calibration, which use observation of ground targets with non-radiating properties such as deserts. But this method requires simultaneous ground observation data. And another issue is uncertainty in the atmospheric correction, because there is the atmosphere between the calibration target on the ground and the satellite. And now we have another method, lunar calibration. And the lunar calibration is lunar observation, and which are free from atmospheric effects, and changes in lunar reflectance over time are negligible, so it's very stable. And the observation opportunities around twice a month, and before after the full moon. We have 2 times in a month. But its accuracy depends on lunar reflectance model we use. And on the other hand, this is very good for the small satellite, but large satellite cannot observe the moon at high frequency because it's very big, so it's difficult to change its attitude to see the satellite. Usually, the sensors are designed to looking down the Earth, so it's very difficult to look at the moon. So vicarious calibration is also used for many large and small satellites, but suitable target site for vicarious calibration is limited because it requires high reflectance and isotopically diffuse, such as desert, and the spatially homogeneous ground surface. And it also requires high frequency of clear skies and dry atmosphere. That is why desert is a very excellent site for this vicarious calibration. And such site has a network. It's called RadCalNet, Radiometric Regression Network, and a network of vicarious calibration sites operated under the Committee on Earth Observation Satellites, CEOS. And data from each site is collected, processed, and published on the internet. So we can utilize the data, calibration data, by log into this RadCalNet. And very famous calibration site in the Railroad Valley in the Utah, in the desert. And the lunar calibration also requires some aspects. We have a chance of before and after full moon when phase angle alpha is more than 7 degrees. phase angle is the angle between the sun and satellite, like this. The light is reflected in the surface, and this is the alpha phase angle. And also, Moon is completely in the field. When Moon is completely in the field of view, we can use a Rolo model. This is a model which is developed by the laboratory in the United States, and it observed the Moon constantly with using a telescope, ground-based telescope. This Rolo model is based on the very large database of the Moon irradiance. And if Moon is only partially in the field of view, we can use SP model. SP model is SP is the name of the instrument on board the Japanese lunar orbiter, and the SP is a spectral profiler on the Japanese lunar orbiter, and this is a model based on such data. And we provide the lunar calibration using the SP model. This is a picture taken by OOC, the ocean observation camera on the right side, and this one is image reproduced by using SP model. So we compare these two images and we calibrate the sensor. So there are data processing levels. So this is a definition of data processing levels. So data levels is, low data is called the level 0, and the levels is going up with the data is processed. And the level 1A is unprocessed data with ancillary data, and the level 1B is radiometrically and geometrically corrected data. And level 2 is atmospherically corrected data. This is a very general definition of the data processing level. It is used in United States, NASA, and ESO. Now we have the LZO data processing like this, and usually the data from the satellite has a noise, and some data packet is lost during the transmission. And this is a picture in some place in the ground, and image of the ground, but there is, you can see the red lines. This is a lost packet data. So these data are lost. And we also have the another data set of the same image, but now we have another lost packets here. So we combine these two data sets and we can get complete image. So such kind of the process is automatically processed in our satellites. And the level 1 and higher level data processing is like this, and there are many steps, and radiometric correction and geometric correction and so on, atmospheric correction and so on. This is a picture of geometrical correction. This is automatic georeferencing. This picture is a base image, which is available from the freely available. And this is a picture image taken by the Sentinel-2 satellite, and this small one is a image taken by OOC on the right side. So we use image matching for these two images, and we can georeferencing of the OOC image by using this base image. So such kind of the processing is automatically processed. And the other important thing in the satellite operation is data management. We also developed the satellite data manager, SDM, and this is an interactive map of the data we we take we took on the Earth, and these small icons are shows the number of images taken in the taken by the OOC, and the color shows the number of images, and so if we enlarge this map, we can see and click the icon, we can get the data stored in the database like this. So we are university, and we don't have such very big budget to buy such kind of system. So we developed such kind of data management system by ourselves. Okay, I'd like to conclude my talk. When designing an optical sensor, it is necessary to carefully examine the optical characteristics of the observation target and select the optics and detector suitable for the observation. When installing an optical sensor on a small satellite or CubeSat, it is necessary to conduct tests to confirm its optical performance in addition to environmental tests. Even for small satellites or CubeSats, observation data from optical sensors are large, so it is advisable to plan data processing and management well in advance of the launch. So, thank you very much.
Yeah, thank you so much. And any questions from the audience? I want to remind the audience that because what Professor Kurihara talk about in this lecture all came from his own experience, because he talked about the things that he had to do it himself, single-handedly. So he learned everything, I think, from the hard way. So I mean, he did not have a big team, and they're all just his two hands, I suppose. And so he had been working very hard on the RISET mission. That's where I met him, get to know him. So talking about RISET, is there any follow-up mission for this very interesting microsatellite initiative, or that it has more or less finished? I cannot hear you.
So, sorry, we have a chime.
I heard that. So it's all right. So it's class Annie. Yeah. I was asking, any follow-up mission for the microsatellite mission called RISET?
Actually, we had a similar project, and now I don't know about the Hokkaido University's project, but I also involved now in another satellite project of the other universities.
And because in the RISET, the mission plan, I remember that you talk about it's very important for to monitor the forest wildfires in South Asia.
Yeah.
Has that mission been? I mean, has that been kind of accomplished, or did you get any results, or thinking that will be continued in future?
Actually, in the case of the RISET, the RISET has unfortunately lost its attitude control system just after the 6 months of the launch, and so it's very difficult to get data from the HPT, because HPT is very high spatial resolution sensor, so it requires very high level of the attitude control, and so we don't have much data from the HPT.
But how about the ocean color imager?
Yeah, ocean color imager has many data because it doesn't require high high level of the actual control. So we have how many? I don't remember, but many data set, and we use it for the analysis of the, what can I say, aquaculture, and the also how can I say, red tide of the ocean.
Yeah, I think it would be very interesting to analyze some of those data and compare with other observations to see how good the the image you have on RISET performed, because it's a very small one, only 1 kilogram, right? If I remember correctly.
Yeah.
So, any other questions from the audience? I mean, it's a good opportunity to learn from to ask Kurihara-san, because he has very how to say, rich experience with microset operation. And then remember that he used to show a diagram comparing the resolution, because okay, there's one. Is that there's one question? I cannot see that. Yeah, there's a diagram showing that comparing the resolution with the size of the satellite, and he always was very proud to show that the HPT and RISET occupy very unique place.
Yeah.
And but that HPT, I think it was a time that we talk about. That was almost the time that the Pennant Lab, the the CubeSat, right, came about, and they also had now a 2 meters resolution.
Yes.
So it's almost as good as HPT, but now it's working very well.
Yeah. Actually, the Planet CubeSat is very high resolution, but they also have they still have 8 bands. So in the case of HPT, we have many bands. So there are different sensors. So it can be applied in different applications.
And this liquid crystal filter work very well. Is that right?
Liquid crystal filter?
Yeah. I mean, the one you have been using on your UAV.
Yes. We also developed the multi-spectral sensor for UAV. It's very small, and we can install it in UAV. And
the liquid crystal tunable filter came from you, or from you bought it from other company?
It's developed by Junichi Corporation in Japan.
You mean the Finnish company? Yeah.
No, Japanese company. Junichi is a Japanese company.
Okay. All right. Any questions? Let me see. Do we have any question in the chat box?
No.
No. Then if not, and I want to thank Kurihara-san for this very detailed lecture on his work on the microset, right, with remote sensing systems, which will be very valuable, because we are also in Taiwan. We also developing this kind of technique, and I hope that someday you will be able to visit us, and we discuss the questions or problems in person. And looking forward to that. Yeah. Thank you again.
Thank you. Thank you very much.
Thank you very much. Bye-bye.
Bye.